So I'm Imran, and this is Team Excobot, and we'll all introduce ourselves.
Hi, I'm Chris Eiler. I'm a full-stack developer.
Hi, my name's Simon. I'm an architect.
Hi, my name is Boris. I'm a full-stack developer.
My name is Don. I'm a software tester and a developer.
Thank you. We have a couple of people who are also on our team but had to leave a little bit early. So let's talk about automation. Let's talk about the job site for a little bit. So you have these workers on the job site, right? And you have these pre-existing machines. You have dozers, you have excavators, whatever the big heavy construction equipment is that you would typically see on a job site. So a lot of that stuff has been bought a long time ago. Maybe you need to go to Home Depot to rent it or whatever, right? So what we decided to do is focus on adding both remote control and autonomy to existing construction equipment. We think this will reduce accidents because, you know, someone who's not in the cab when the thing tips over, like the crane that just happened here, is someone who doesn't get hurt. We think that this will reduce costs because, you know, that's some additional time that you can get per day where the shovel can dig itself, right? And we just think it's a good overall benefit to the industry. So we decided to build a platform to automate an excavator. We actually, you know, got some hardware. We have some, all the stuff is going to fly around here. Yeah. We have some, you know, this is an upboard. It's a pretty powerful computer, some depth cameras and stuff like that. And then we got to work on making that a reality. With that, I'm going to hand off to Chris over here, or to Simon, who's going to show you the mechanicals of how it all works.
Hey, everybody. So if we just press play here, we can see our Caterpillar that you can get at any Home Depot and rent. You can see our mechanism attached to the mini excavator, where you can see we have our forward motion. Is that playing?
It's not updating. I think that was the USB that got pulled.
Oh, really? Okay.
Yeah. So,
Just having a bit of a hardware glitch, guys.
Oh, because you're playing from the
Just one moment.
yeah, just give us a little technical difficulty here. Can you? Yeah.
So just while we wait for that, the mechanism you can see is mounted on the front, and that mechanism on the front, you can see the V-rail sections, and they connect. What we have is a Bluetooth box and a stepper motor connected to like a NEMA 17 or 23 motor that is connected to a pulley system to manipulate the tracks, left and right tracks, the front. So you can see it at the front there. We'll just take the roof off so you can get a better view of inside the cab. So we'll just rotate there. So you can see we've got that front mechanism that's manipulating the left and right Caterpillars, and then on the back next to the cabin is the manipulators for the scoop at the front and the arm as well. So there's actually only two mechanisms, but we've got two of them, you know, two of those back ones are exactly the same. And that's the mechatronics of the project. Let's hand it over to Chris.
Thank you, Simon. I'm Chris Eiler, a full-stack web developer. We're working on the front end. Boris was there as my teammate. And so after we have the brain box on the excavator and the control mechanisms to feed from the brain box, what we now have is a front-end website, and we would take the camera input, we'd stream it to maybe a tablet or some endpoint, and where our user is physically holding it with a touchscreen ability as well. And you'd be able to see what's happening in real time up there. And we're ready for video 2 or video 3. Which now we're going to go through some of these front-end controls, which are touch sensitive. The first one we have here are the actual arm controls, which will be things like the bucket, then the elbow, and then the actual shoulder, which can go up, down, left, right. And so we have those on the outer controls over here. Oh, that's the initial video of us, me, and we're ready to go to the next video. And that's me begging for a job. So if you're hiring me and Boris, or interested. So here, when you press these buttons, what we have is up here is our state, and what that is measuring is your full extension or contraction of one of the limited range of motion tools. For example, the bucket that's lifting can only go so much of the one way and so much of a constriction. And so a 0 would be fully constricted, and 100 would be fully, expanded. And you can see at the very top, as I was pressing through the buttons, that was changing. But also over here, you'll see these are our individual network posts that are sent to our brain that's ready to receive those and can interpret the bucket object and at what level it's supposed to be expanding or contracting in real time. So we're ready to go to the next one, which will be our left and right tracks, the next video, video 4, I believe, our last video. And so the unique thing about the components was a little bit easier because they have a limited range of motion, and we can go from a percentage rate of fully expanded to contracted. But things like our tracks here, since those have no limited range of motion, they're a circular motion that can continue going, what we have is speed ratings. And what we have is the top groups are our forwards and the bottom groups are our back. So it's very thumb orientated towards moving forwards and back. And we'll take those speeds, and you can see here again our individual speeds down what is here usually is like the speed object right there. This is our object that our brain box is expecting to receive, which has speed, direction, and which track that's actually moving. In addition to that, one of the key parts about how we have to design this feature is, so you have to press down on the button in order to initiate speed, but it's sensitive for an event listener. So the moment you stop pressing on it, it sends a follow-up network post to say, hey, stop the track. So one's the initial start, and then once you press off, it tells it to stop. And that's the basic functions and interactions on the front end.
All right, and so that gives you pretty much the idea of what we did, right? The nice thing about doing it this way, by having this intermediate layer going to our brain, is that now machine learning can also be put into the cloud, and it can take over control. So your operator, as he or she operates your equipment, that equipment now learns how to be operated by itself. You can record a macro and say, hey, always do this motion. That's easy. The vision systems are there, so you can put on vision-based learners. There's also a LiDAR system, so you can actually have it begin to drive around and clear cut or whatever it is that you need the equipment to actually do. With that, we'll open to questions.
So I guess can you just clarify for me, what is the industry problem that you're solving, and who is kind of the person benefiting from this?
So the initial thought here was most of the existing equipment that's already been bought is not already autonomous or automatable, right? You go to Home Depot, you can't buy an autonomous excavator. You can't rent one either, right? So this allows you to take existing hardware and make it smart. So you could take you've got your Doug's excavation firm, right? You do house residential kind of stuff. You don't have the $500,000 autonomous digger, but you can go now, Home Depot, get our thing, and automate your digs. Now you can do 2 or 3 jobs at the same time, so just the one.
Not having autonomous doesn't sound like a problem.
Not having time. I've done digging, and I found it to be really boring when I've done it. And I was making the thing of, I could go away for an hour because I've already set up. Why am I just doing D, when it took me 2 days for the job I did, and half of that time, the machine could have done the work itself.
One way I'd like to put it is when we're talking about these controls here, it won't take long before you're like, I'm pressing the same pattern controls 20 times for this plot of land or for, let's say, a long tunnel trench. Now, once you realize there's a pattern, it wouldn't take long to press a set button and just set that pattern, and now you just are responsible more for monitoring that while you look at your next project, and then eventually you're monitoring 3 projects at once, rather until you have a specific new use case. But on recurring use cases, this can scale relatively easily.
One question I have is not so much on what you guys have presented, but did you have any discussion on, so let's pretend that, or not pretend, this is all operational, it's all functional, it's all fabulous and all that, but what's the workflow from, oh, I need to dig a basement on that piece of property to get that programmable and the machine to be able to understand what it needs to do? Did you have any of that discussion? I'm not saying there's a right or wrong answer here, I'm just curious.
We didn't really have a lot of that discussion because this is just a hackathon prototype kind of deal. The idea here is if you do actually have this for real, there are GPS and other kind of things already out there. So you would probably drive a normal traditional truck, drop off the equipment, have GPS waypoints, and then it would do its thing, just like the workflow on real autonomous sites now. Big companies, Mortensen has autonomous excavators, for example. They already buy this. They already do this. So we would just copy those existing workflows and just rephrase them for smaller companies.
And one other question, did you have any discussion on the breadth of operations, equipment types that you saw this exact tool being able to be adapted to? Or is it just like that excavator, or what are your other, do you have any other ideas?
The specific control mechanism that you see, this part here, the sensor platform and control platform is totally generic. Could be put into a Tesla if you wanted to, right? Could be put into a submarine. Could be put into anything that could be, anything that has control surfaces available to it. The thing that you'd have to change per vehicle type is that framing that you saw. That would have to be adapted per type or per vehicle, which is actually not that expensive or hard to do.
And after we do a couple, there's some common features, like joysticks, how to do the next joystick on the next vehicle, or the steering wheel on the next steering wheel item after you've done another one, or pedals, for example. There's a level of repetitivity of this after a few implementations.
How much of this was done this weekend? I mean, was you coming to build on top of anything, or did you
All of it.
start from scratch?
We, other than having bought the equipment,
Yeah.
all right, that was.
Did you manufacture this?
No. We actually did put the wires in the breadboard. Yeah, no, we wrote all the code and did all the mechanical drawings and everything. This is pure weekend work.
Great. Thank you.
I think they're trying to wrap us up, but we'll take one last question.
Okay, thank you. The CAD model that you showed of the excavator,
Yes.
was that just for display purposes, or is it built into this idea that
That's a real excavator. That is
it's a real excavator
that's
and you could use that
that's a real CAD model from a real excavator. That is the real
machine
deal.
learning, you could hook it up and train?
Oh, that was just for the drawing. That's a pure CAD model,
Okay.
right? We didn't we don't have a simulator, if that's what you're asking,
Right.
where you could train in simulation. But there are already existing simulation environments from OpenAI and
Yeah,
other
that's
places
what I'm
like that.
aware of.
We just haven't plugged those in
Treat
yet.
a robot by putting a robot on the screen, and then once it knows how to do it, then you just download the code into the robot.
But the model should be exportable to that format. We just haven't tried.
Okay.
Okay, that was our last question. I think we're done. We're out of time. So thank you all.